Hi, this is week 32 of AP Physics, and we're working through Unit 9, which is DC circuits. In this lesson, we'll be looking at resistors in parallel as well as resistors in a circuit. For our lesson objective says students will learn how to calculate the current in a circuit when resistors are in parallel. As well, we'll be looking at circuits involving series and parallel as well. Let's go ahead and get started.
Let's begin our lesson on resistors in parallel. Now, in the picture on the bottom right, you see a couple of light bulbs. Those are our resistors. They're connected to a battery. The setup is a parallel setup, so that the wire goes from one bulb to the next. Now, when the resistors are connected in parallel, the potential difference across the resistors are the same because each is connected directly across the battery. When the current reaches a junction point, like for example, junction point A, let me go ahead and put an arrow up to it on the diagram, that current will go ahead and split. So now we have the current 1 and current 2. Now the currents may or not be equal. Usually they're not equal. If both resistors are of the same resistance, then the currents will be the same. But likely the two resistors will not match, so therefore the two currents will also not match. Because the charge is conserved, the current I that enters the point A, where the junction is, must equal the total current. So if we add up current I1 and current I2, that will equal our initial current that went into the junction, as you see in the formula here. Now, the value of an equivalent resistor, Req, is given by the following formula, which is the inverse of Req, the equivalent resistor. And that is equal to the inverse of resistor number 1 plus the inverse of resistor number 2.
Let's go ahead and take a look at example 6. We're asked the following. 3 resistors are connected in parallel. A potential difference of 18 volts is maintained between point A and point B. Now they ask us the following questions. Find the current in each of the resistors. So for part A, we're going to go ahead and use the following formula. Is the current is equal to the potential difference over the resistance. Alright, so for each one of those, we're going to go ahead and solve for resistor 1, 2, and 3. And we're going to go ahead and plug them in as such. So for current for number 1, it's going to be potential difference of 18 volts over our resistor, which is 3 ohms. Okay, so that's going to go ahead and give us 6 amps. For number 2, it's going to go ahead and be 18 volts over our 6 ohms. So it's going to go ahead and give us 3 amps. And for the current of number 3, it's going to go ahead and be our 18 volts over our resistance of 9 ohms. So that gives us 2 amps. Alright, so that is the current for number 1, 2, and 3. That's part A. In part B, we're asked the following. Calculate the power delivered to each resistor and the total power. Alright, so now for part B, it will look like this. Power is the current times the voltage. So I times delta V. So we have the current for each one of them. So they want the power delivered to each resistor. And then we're going to get the total by adding each of the resistors together. So it's going to be for number 1. What's going to go ahead, well, let me go ahead and do this actually right below. P1 is going to go ahead and be the I, which is a current of 6 amps times the voltage of 18 volts. For the power for number 2 is going to be 3 times 18 volts. And the power for number 3 is going to be 2 amps multiplied times the total potential difference. Alright, so now we get 6 times 18 will go ahead and give us 108 watts. 3 times 18 is going to go ahead and give us 54 watts. And 2 times 18 is 16 watts. Now, they asked us also not just for each one, but also the total power. So to get the total power, just go ahead and add all of them together. So that's going to go ahead and be 198 watts. And that will be your total power. In part C, they ask you to find the equivalent resistance of the circuit. So we got the three resistors of 3, 6, and 9 ohms, what will be the equivalent resistance? So let's go ahead and do that next. So for part C, it will be equivalent resistance is the inverse of resistor number 1 plus resistor number 2 plus resistor number 3. So that's our formula. So let's go ahead and substitute our values in. Equivalent resistance is equal to, our first one is 3 ohms plus, we're going to have 6 ohms plus 9 ohms. Alright, so now I'm going to go ahead and get my calculator and get the decimals for all of these guys. So 1 over 3, 1 over 6, 1 over 9, and so that's going to go ahead and be 1 divided by 3. It is 0.333 plus 1 over 6 is going to give us 0.166 plus 1 over 9 gives us 0.111. So now I'm going to go ahead and add them all together. So my equivalent resistance will look like this. So the inverse of my equivalent resistance is going to be, add all of these values together. 0.111 plus 0.333 plus 0.166 gives us 0.61. Alright, so now I'm going to go ahead and move stuff around a little bit so I can go ahead and isolate my resistance. So it will look like this, 1 over 0.61, that's my equivalent resistance. So my answer for this problem is going to go and be, I'm going to round it off to 1.64. 1.64 ohms is my equivalent resistance for our 3 resistors. Alright, so that goes ahead and takes care of part C. Now let's go ahead and take a look at part D. Here it says find the total power delivered to the equivalent resistance. Alright, so for that one, the total power, we can go ahead and get the total power by getting the potential difference squared over the equivalent resistance. Alright, so as we plug them in, the equivalent resistance, potential difference squared over equivalent resistance will look like this. This will be part D. So that's going to be 18 volts squared divided by 1.64 ohms. Alright, so 18 squared divided by our answer gives us 198 watts, which matches part B we have previously solved for the total. Alright, so just another way of solving for the total. So whether you solve for them individually like we did in part B, or we use the equivalent resistance, we can still get the total power from any one of those. Alright, that takes care of example 6. In problem 20 we're asked, if a 4th resistor were added in parallel to the other 3, as from the previous problem, example 6, how would the equivalent resistance change? Alright, notice that they're inverses of each other. So if we add another resistor, add more resistance, the equivalent resistance would be smaller because they are inverses of each other. So more resistance, lower equivalent resistance. Alright, that is problem 20. In problem 21, we're asked the following question. Suppose the resistance on example 6 were 1, 2, and 3 ohms, respectively. A new voltage source is provided. If the current measured in the 3 ohm resistor is 2 amps, then A, find the potential difference provided by the new battery and the currents in each of the remaining resistors. Alright, so we're going to go ahead and use this formula to go ahead and solve for what is the new potential difference provided by the battery. So we're going to go ahead and rearrange it, move the resistance here. So the potential difference is going to go to be I multiplied times R, where we have I, they tell us that the current is 2 amps. So we're going to go to multiply that, 2 amps. Multiply times the resistance, let's set the resistance for the 3 ohm resistor. So that gives us a current, a potential difference of the current times the resistance of 6, and that's voltage, so volts for the potential difference. Alright, so now we got the potential difference. Now they have a follow-up question. After you do that, also find the currents for each of the remaining resistors, for the first and second resistors. So what is the current for each one of those? We're going to go ahead and use this formula for resistor number 1. It's going to go ahead and be the potential difference of 6 volts over 1 ohm. So that gives us 6 amps. And for current number 2, that gives us 6 volts over 2 ohms, so that gives us 3 amps. So that'll be the current of the other ones, and again, number 3 was given to us to be 2 amps. All right, so that takes care of part A. In part B, they go ahead and they ask us, find the power delivered to each resistor and the total power. All right, so for power we have the current of each and we have the potential difference. So we're going to go ahead and use this formula. So this will be part B, this was part A. All right, so power for the first resistor, it was I, the current, which is 6 amps, multiplied times the potential difference, which is 6 volts, so that's 36 watts. For number 2, it is, again, number 2 is actually 3 amps, multiplied times 6 volts, so that gives us 18 watts. And finally, the power for number 3 would be, it was 2 amps multiplied times 6 volts, so that gives us 12 watts. Alright, so that is the power for each of the resistors. Now, the total power, all we got to do is go ahead and add them together. So it's going to go ahead and be, that's 66 watts. That is our total power, 66 watts. Alright, that's part B. Next, in part C, they ask you find the equivalent resistance for this setup. Alright, so for our equivalent resistance, it's going to go ahead and look like this. So it'll be the equivalent resistance is equal to the resistance of the first plus the inverse of the second plus the inverse of the third. Alright, so now we're going to go ahead and substitute their resistance 1, 2, and 3. So it'll end up looking like this. Once we substitute, 1 over 1 plus 1 over 2 plus 1 over 3. Alright, so let's get the value for all of these. So put them into your calculator, and 1 over 1 is just 1, plus 1 over 2 it is 0.5, plus 1 over 3 it is 0.333. Alright, let's go ahead and add them all together. So it's going to go ahead and give us 1.833, and after to solve for the equivalent resistance, what we're going to do after this is we're going to go ahead and get the inverse of this value. So the equivalent resistance is really the inverse of 1.833. So that gives us a 0.54 ohm equivalent resistance. Alright, so that is the answer for part C of this problem. Now in part D they ask you, can you find the total current and the power by the equivalent resistor? Alright, so we're going to go ahead and do that. What is the total current? So we're going to go ahead and use this formula. We have the equivalent resistance right there, and we have the voltage. So let's go ahead and take care of that. So the total current, it's going to go ahead and be the potential difference over the equivalent resistance, which is 0.54 ohms. So it'll be 6 divided by our answer, which is, we're going to go with 11 amps. Alright, so that will be our total current. Now again, they also want, we want the total power. Alright, so power total, that is our 11 amps, multiplied times our potential difference, 6 volts. So that gives us 66 watts, which again, we had solved for it in part B, but in part B we used their individual power and then added them together. Here we just had the total current, and we'll use this formula to get the total power. Alright, that takes care of example, or actually problem number 21. In problem 22, you're asked the following question. Suppose you have 3 identical light bulbs, some wire, and a battery. You connect one light bulb to the battery and take note of its brightness. You add a second light bulb, connecting it in parallel with the previous light bulbs, and you take note of its brightness. Repeat the process with a third light bulb, connecting it in parallel as well with the other 2. As the light bulbs are added, what happens to A? Let's start with the brightness. Does it increase, decrease, or remain constant? What about the individual currents to each of the bulbs? Increase, decrease, or remain constant? What about the power delivered by the battery? And what happens to the lifetime of the battery as you add more bulbs? To answer A and B, we're going to go ahead and refer back to our notes at the very beginning of this lesson. And in it, here's right here, it says when the resistors are connected in parallel, the potential difference across the resistors is the same because each is connected directly across the battery. All right, so it's the same. So for that reason, going back to our problem, it's the brightness is going to go ahead and remain constant. Also, the individual currents, again, each individual connected in parallel is connected directly to the battery, so the individual currents will also remain constant. As you're adding more and more bulbs, they're going to remain constant. Now, part C, they ask you, what about the power delivered by the battery? Now, that's going to go ahead and increase. Why is that? Well, the total current, as you add one more bulb, and then you add another, and then you add another, notice that you're increasing the total current, and that's going to go ahead and increase the total power. So for that reason, for part C, that will increase. And in part D, they ask you, what happens to the lifetime of the battery? Well, if you're drawing more power from it, the lifetime is going to go ahead and reduce. So it's going to a lot less. So it's going to go ahead and decrease. Or it's going to last a lot less. All right, that is the answer for problem number 22. In problem 23, we're asked the following. If the light bulbs in problem 22 are connected in series as opposed to being in parallel, what happens to the brightness, the individual currents, the power delivered by the battery, and the lifetime of the battery? All right, so now notice that they are now in series. So let's start with the brightness. All right, so the brightness would actually decrease. So I'm going to go ahead and write that down. What happens to individual currents? That would also decrease because the resistance is increasing. What would happen to the power delivered by the battery? Well, if the current's decreasing, the power will also decrease. And what happens to the lifetime of the battery? All right, well, you have a slower current, so therefore less chemical potential energy is being used, so therefore the lifetime of the battery would increase. All right, that is problem number 23. In example 7, we're asked the following question. 4 resistors are connected as shown here. And they ask you to find the equivalent resistance between point A and point C. All right, so we're going to go ahead and do that. Now, in this diagram, the first 2 resistors are in series. All you have to do is add them together to get the equivalent resistance. But the third one is in parallel. So we're going to begin here solving for the equivalent resistor of our parallel. So I'm going to go ahead and the formula for the parallel is going to be 1 over 6 plus 1 over 3. So this is 1 and 2, here they are, 1 over 6, 1 over 3. Go ahead and divide them and add them to each other. You end up for the equivalent resistance for the parallel, for the P for the parallel, it's going to be 0.5. And now you go ahead and you rearrange them. So it's going to go ahead and be 1 over 0.5, which will give us 2 ohms. So that is equivalent resistance for the parallel section of our circuit. Now that we have the equivalent resistance for this section, which is 2 ohms, we can go ahead and now add them all together to get the total equivalent resistance for the whole circuit. So that's going to go ahead and be 8 ohms plus 4 ohms plus, from the parallel section, remember it was 2 ohms. So we add them all together, we end up with 14 ohms as our equivalent resistance for the whole circuit. Now in part B, they ask you, what is the current in each resistor if a 42 volt battery is connected from point A to point C? So we want the current. So we're going to go ahead and use the following formula. I equals delta V over R, where we have the potential difference is 42 volts. That's our numerator. And our equivalent resistance of 14 ohms goes in the denominator. So 42 divided by 14 gives us 3 amps. So that is the current for the first resistor and for the second one, who are in series. So let's go ahead and write that down. That is 3 amps here, 3 amps there. But now what happens to when we reach this point where we have a junction? Now the current's going to decrease. Some of it's going to go up, some of it's going to go down. So we're going to label this one I1 and I2 for their current. Now, what we need to find is what is the potential difference at the junction, because we've already gone through 2 resistors. Alright, so to do that, we're going to go ahead and set it up so that we have our same formula is going to be I times R. So that's going to go ahead and be, for the I, we're going to go ahead and put our 3 amps, and our resistance for this part of the circuit was 2 ohms. So that gives us a potential difference of 6 volts for this part of our circuit. Alright, so now we have that, we're going to go ahead and plug it into this formula one more time to figure out the current for I1 and I2. So I1 is going to go ahead and be potential difference over the resistance, resistor 1, let's call it this one. So it's going to be 6 volts over R1, which is 6 ohms. So this one will have a current of 1 amp. Alright, and resistor 2, it's going to go ahead and be the same formula, but for the second resistor, alright, it's going to be 6 volts, and the second resistor, it is 3 ohms, so that gives us 2 amps. Alright, so the current for this one will be 1 amp, for this one will be 2 amps. Notice that both of them together equals 3 amps, which was the current for the other resistors. Alright, that takes care of example 7. In problem 24, we're asked which of the original resistors displaces energy at the greatest rate. So we have 4 resistors here. The answer would be the first resistor that has 8 ohms of a resistance. So the greater the resistance, the more it will dissipate energy. In problem 25, we're asked, suppose the series resistors are now 6 ohms and 3 ohms, while the parallel resistors are 8 ohms and 4 ohms, and the battery is now 27 volts. So with all of that information, now they ask us find the equivalent resistance. Alright, that's part 1. And in part 2, it says find the current and for the total, and as well as 1 and 2. Alright, so let's go ahead and do that. Let's begin with the equivalent resistance. Again, we have our circuit. This part is in parallel, so we're going to go and find the equivalent resistance for the parallel first. Alright, so the equivalent resistance for the parallel is going to be 1 over 8 plus 1 over 4. So that's going to go ahead and give us the following. The equivalent resistance is equal to, let's see, 1 divided by 8 plus 1 over 4 gives us 0.375. And now we get the inverse of that. And we end up with 2.67, and that is our equivalent resistance for the parallel section. Now we want the total for the whole circuit. It's going to be, this is series, that's in series, and now we're going to treat it as being series when we get the equivalent. So we just add up all 3 of them. So the equivalent for the whole circuit is going to go ahead and be 6 ohms plus 3 ohms plus 2.67 ohms. So it's going to go ahead and give us 11.67 ohms. Alright, so that is part A, the equivalent resistance for the whole circuit. Alright, now in part B, we're going to go ahead and solve for the current. Alright, so what is the current now? So we have the following. I equals delta V over the equivalent resistance. Alright, we know that the voltage was given to us in the previous slide. It was 27 volts. Here we go. So we're going to plug that in as our numerator. So it's 27 volts over the equivalent resistance for the whole circuit, 11.67. So that's going to go ahead and give us 27 divided by 11.67, 2.31 amps. Alright, so that'll be the current here as well as here, since they are parallel, 2.31 amps, 2.31 amps. Alright, now what about here? Notice again we have a junction, so the current's going to go, some's going to go up, some's going to go down, and also what we're going to need to find is the potential difference at this point. Alright, so the potential difference at that point, we're going to go ahead and use the following. We're going to have potential difference is equal to I times the equivalent resistance, but the equivalent resistance for the parallel part, so I'm referring to that one. So it's going to be delta V is equal to I, 2.31 multiply times the equivalent resistance for the parallel section of our circuit. So that's going to go ahead and give us the following times 2.67. It's going to give us, we're going to round it off to 6.18, and that is our potential difference for that part of the circuit. Now we have that, we can go ahead and use this formula again for I1 and I2. So it'll look like this. I1 is equal to potential difference, which is 6.18 for this part of the circuit over the resistance of 8 ohms. And for I2 will look very similar, same potential difference. And this resistor. Alright, let's plug them into the calculator. So this is going to go ahead and give us 0.77 amps. And for I2 is going to be 6.18 divided by 4 is going to go ahead and give us 1.54 amps. Alright, and that will be the current for the top resistor and the bottom resistor. Here we go. These are our answers. Alright, now if you go ahead and take a moment to add them together, so let's go ahead and do that. 1.54 plus 0.77 is going to go ahead and give us 2.31, which matches the current of the circuit while it was in series. Alright, that takes care of problem number 25. In problem 27, we're asked the following question. When the switch is open, power PO delivered to the resistor 1, here it is, when the switch is closed, which of the following is true about power PC delivered to R1? Alright, so now we're going from one single resistor to two resistors once we close the switch. So now, what happens to the power delivered to R1? The power will remain the same. Remember that here they're being connected as parallel, so therefore the brightness of a bulb will remain the same, so therefore the power being delivered remains the same. That's why the answer is B. In problem 28, we're asked the following question. Find the current in the 12 ohm resistor below. Alright, so we're giving this schematic right here, and they ask us to find the current for it. Alright, so here we have it. What we're going to go ahead and do is start reducing it, and here we have step by step by step by step until we can get just one equivalent resistor for this whole diagram, and then we're going to go ahead and find the current for the whole circuit. So that's where we're going to go ahead and start. So let's start here by reducing these two parts of the circuit that are in parallel. So since they are in parallel, we're going to go ahead and use inverse. So it's going to be 1 over 6 plus 1 over 6. And then the inverse of that is going to go ahead and give us 3. So this section right here, now I'm going to go ahead and put it in red, now becomes 3 ohms. Again, this part is that right there. That's the equivalent resistor for this section of the circuit that was in parallel. We're going to do the same right here. It's going to be 1 over 4 plus 1 over 12. And then that's 0.333. Then we get the inverse of that, and that is 3 again. So it's 3 ohms. So both this was 3 and that was 3 as well. Next, since these two are in series as well as these two, we can go ahead and just add them together. So 3 plus 3 will give us a 6 ohms. And this one, 3 plus 2, that will give us 5 ohms. Now, we can reduce it some more. These two are in parallel. So we're going to go ahead and find their equivalent resistance for that section. So it's going to be 1 over 6 plus 1 over 5. That gives us 0.36. We get the inverse of that. And we give us 2.73. Alright, so that's what we got. Now, these two are in series with each other, so we just add them up. So we have our 5.73, and that is our ohms, the equivalent resistance for this whole circuit. Now we have that, we can go ahead and now calculate the current using the equivalent resistance. So that's going to look as such. It will be, the current is going to be equal to the potential difference divided by the equivalent resistance. Alright, so now the potential difference was 18 volts that was given to us. And the equivalent resistance of 5.73 ohms. So 18 divided by 5.73 gives us 3.14 amps. Alright, so that is the current through the circuit. Next, what we're going to go ahead and do is we're going to get that and find, so as the current's going through here, what happens once we reach this first junction, and we also have a second junction to deal with here on its way to the 12 ohm resistor. So the current through here is going to be 3.14 amps. All right. But right here, we're going to go ahead and it's going to go I1, and let's call this guy going down I2. We don't really care about I1. We're really interested in I2 going down as we went through the junction. So let's go ahead and solve for that. All right. So I'm going to erase a little bit of this. All right. So what is the potential difference at this point in our cell? All right. We know that the current is 3.14. And we know that the equivalent resistance for both of these parts is, oh, I erased it. Let me go ahead and write it down one more time. The first junction, it was 1 divided by 5 plus 1 over 6. And the inverse of that, it was 2.73. So let me go ahead and put that down again. 2.73 ohms. Alright, so that's the equivalent resistance going in for this junction. So that's that one. Alright, so again, what we're going to go ahead and do is find the potential difference for this part right here. So that's going to go to be current is equal to potential difference over resistance. So we're just going to go ahead and get the potential difference by multiplying the I times the R. And the current was 3.14 amps. And we'll multiply it times the equivalent resistance of 2.73 ohms. So we end up with a potential difference at that part of the circuit, and that is 8.56 volts. All right, that's at this junction right here, which is that section there, which is this one right here. All right, so now we have that again, it's going down. So now we're looking at that one. So we have the potential difference for this section, but we want what is the current going down the junction where we labeled it I2. All right, so for that, that's going to go ahead and be, the following is going to go ahead and be current is equal to potential difference over the resistance. And the resistance for that one is 5, so therefore it's going to be 8.56 volts over 5 ohms. So the current is 1.71 amps. Alright, so that's going down this side. So we got in it. Now we know that going down, so this I2 right here, it's equal to a current of 1.17 amps. Alright, now here we go. We have another junction right there. Alright, so another junction, so it's going to go ahead and split. So now we got to go ahead and solve for that. So it's going to look very similar where we ask, well, what's the potential difference at that point, at this junction right here? Notice that again, this junction, that is our equivalent resistance for it. It was 3. We had solved for it previously. Alright, so now we have the current and we have the equivalent resistance, so we can figure out the potential difference at that point. So the potential difference, again, it's going to go ahead and be I multiplied times R. And the I is 1.71 amps. That was a current at this part. And the equivalent resistance was 3 ohms. So that goes ahead and gives us a potential difference of 3 times 1.71 gives us 5.13 volts. Alright, so that's the potential difference at this point in the problem, in our circuit. Now, again, it's going to go down. We're going to call that I3. It's going to go down and up, but we don't care about the one going up since they asked in the question for the 12 ohm resistor. Alright, so what do we do now? We're going to go ahead and put this. This will be I3 is going to be the potential difference divided by the resistance. Alright, the potential difference was 5.13 volts divided by the resistance of that resistor, which is 12 ohms. So that's going to give us 0.43 amps. And that is the answer for problem number 28. This brings us to the end of week 32, unit 9. Thank you so much for watching.